Hello everyone, uh, welcome to my channel. So in this video I am going to talk about electrochemistry and also CH functionalization. Okay, let's begin. So our sole goal is doing chemistry is making sustainable world, making better world in sustainable way. University and also research institute and industrial companies are investing money uh, to achieve this goal in more effective and simple manner. So today I'm going to talk about one of popular method that we can use to do used to make a better environment, that is transition metal catalyzed electrochemical oxidative CH functionalization. So in this presentation actually I have combined two concepts that in chemistry, that is electrochemistry and CH functionalization. So first of all, let me give brief introduction about the CH activation. As we know, using traditional chemistry like pre-carb alkylation, acylation, and also cross-coupling reaction, so we can make a new CC bond. But cross-coupling reaction has been used more widely in past few decades, even in industrial scale. So, but what the problem with this cross-coupling reaction is, so we have to install this kind of halide and also boronic, as we need to synthesize this kind of boronic acid to get to do this kind of this chemistry. Uh, that's actually, so we have to pre-functionalize those things. That's the bigger disadvantage of this cross coupling reaction. And also we can so during this reaction, so stoichiometric amount of waste can be generated. And also one other problem is using harsh condition like high temperature. That's a big disadvantage in this kind of chemistry. So therefore people always looking for new alternative method for this cross coupling reaction to make new CC bond. So we can break this CH bond by incorporating with the transition metal catalyst, and then we can make new CC bond. This process actually we call CH activation. So normally we can we can make new CC bond or CX bond, like C oxygen or C nitrogen, that kind of bond we can make. So this process actually we call CH activation. So in CH activation, actually there are a bunch of examples have been demonstrated in past few years, like using rhodium catalyst, ruthenium, palladium catalyst. So those kind of transition metal catalyst has been using. And here I have listed just one example that is that's used palladium catalyst to make new CC bond using this transition metal catalyst CH functionalization. So using actually this strategy, so we don't need to pre-functionalize, so we can reduce step synthesis step using this method, and also waste generation also we can minimize. Another thing actually in this strategies we can improve, because we have reduced step, and so we can improve the atom economy and also step economy using this CH activation. With that, so when we talk about the transition metal catalyzed when we talk about the CH activation, so bond dissociation energy and also pK values is very important. So when we consider radical CH functionalization, bond dissociation is worth to consider. And but when we talk about transition metal catalyst CH functionalization, so we have to consider about the pK values. pK means actually acidity of the CH bond. So as you can see here, is an alkyne bond, alkyne SpCH bond. So you can see pK around 28. This is actually quite acidic when we compare with other CH bond. So it means it's easy to access this CH bond rather than other CH bond. So when we go right hand side in this table, so you can see pK is getting increased. That's mean acidity of this CH bond is getting decreased. So then it's mean actually, so we it's comparable difficult to access this CH bond. So with that, so this all CH bond functionalization reaction we can categorize into two area, that is direct CH functionalization and other one is directing group assisted CH functionalization. So when we talk about the direct CH functionalization, so we are considering electronic and steric effect. So as example, so you can see this benzoic CH bond, so benzylic CH bond, so you can see it's very easy to access than others aromatic CH bond. So here actually in this area, so controlling, this is actually very simple strategy, but controlling radioselectivity is very difficult. And other one is a directing group CH functionalization, directing group assisted CH functionalization. So using this strategy, like we are trying to access CH bond using directing groups such as aldehyde, amine, and carboxylic acid. So this kind of directing group we can use. Using this directing group strategy, so we can access even very close ortho CH bond and also meta CH bond, and also very far away para CH bond we can access. So there are a bunch of examples have been demonstrated related to this directing group assisted CH bond functionalization, like a palladium, rhodium, or ruthenium catalyst have been used. So this in this strategy actually, when we control the radioselectivity, it's very easy to control radioselectivity using this method. But still there are many challenges when we control the directing group. So still there are many challenges to overcome. So as I mentioned in my title, first slide, so I am going to talk about in this presentation, so this video, so oxidative CH functionalization. So here, so this is the general mechanism for oxidative CH functionalization. So you can see in the first step, this is the starting point. So we can substrates coming in, and then so this CH bond is can be broken with this transition metal catalyst. So you can see now we have new bond with transition metal and our substrate. So that's the step we call CH activation, and then our second substrate coming in, and then there is insertion step, and then with reductive elimination, so we can get our desired product. So in this step actually, so this intermediate transition metal catalyst intermediate, so reduced by 2. So then we have to oxidize this intermediate to gain our active catalyst. So this is normally this oxidation we can do using chemical oxidants such as copper or silver salt. But problem is actually here, so when we use copper or silver salt chemical oxidant, so we are generating stoichiometric amount of toxic waste. So that's big disadvantage of this chemical oxidant related chemistry. So in addition, so you can see when we compare with other oxidant, so you can see chemical oxidant has higher price. So that's one also another disadvantage. When we talk about the sustainable approach for CH activation, so we have to minimize this toxic waste generation. So that is the place electrochemistry coming to my topic. So using electrochemistry, actually we can do sustainable CH activation. So we don't need to use any chemical oxidant to access CH bond. There are other method has been demonstrated, but in this presentation actually I am talking about only electrochemical approach for CH activation. So with that, I would like to discuss about little bit background of electrochemistry. So electrochemistry actually very quite old subject. So there are a bunch of development has been demonstrated in past few centuries, and here I have listed few examples that's related that we can do using electrochemistry as a example. So here you can see we uh, can have we can store energy like a battery using electrochemistry, and also energy conversion also possible using electrochemistry, and industrial electrolysis also has been performed using electrochemistry. And other important thing is actually organic electrosynthesis. In here actually in this area we have combined organic chemistry and electrochemistry together. So that is very fantastic. So organic electrosynthesis actually have been using even in industrial scale. So here this is just one example. So lismerol, so that is wonderful fragrance that has synthesized by using electrochemistry. This and also next example actually this birch reduction. So normally birch reduction, so we have to use ammonia for birch reduction, but now we don't, with this electrochemistry synthesis, we don't need to use this painful ammonia to synthesize this kind of molecule. So in 2019, so this birch reduction has been done using electrochemistry. So that is wonderful development in this area. So with actually this organic electrosynthesis actually is very sustainable because we are using electrochemistry, electricity as a source, and because of and also so we can scale up even in industrial scales. So this organic electrosynthesis, that's the major advantage of this organic electrosynthesis strategy. So with that I would like, so here actually I have illustrated, so you can see the development of electro-organic synthesis. So electro-organic chemistry, so starting in 1600, so electrochemistry was introduced, and then slowly it developed up to 1834 until Faraday introduced his Faraday's laws. After that 1848 Kolbe introduced first organic electrosynthesis reaction. So after that actually many development has been performed up to today. So there are a bunch of example has been demonstrated. So today actually, so we have very interesting new strategy that we can synthesize different molecules like a CH activation. So those new strategies now have been combined with electrochemistry to do more sustainable approach for synthesis. So with this introduction, so now I would like to talk about how electrochemical reaction is working. So this is the general setup for electrochemistry electrochemical reaction. So you can see it has two electrode, anode and cathode, and then it connect to the external power source, and then also we have our electrolytes and reactant and catalyst. And then next step actually, so when we convert to the system external power source, so electron pull from anode and then push into the cathode. So in this situation actually electrode potential can be generated between these two electrodes. So actually this electrode potential is help for the redox reaction. And then actually next step, so electron start to move through this line, and then this iron species is moved toward to electrode. So this process actually we call, this complete process we call current. And then last step actually, so we are going to have our redox reaction. So you can see electron moving through this line, but electron cannot move this solution through solution. So therefore we are using electrolyte. Those are charge species. Charge is this, with electrolyte we can continue our reaction. So actually in this situation, so electrolyte and we have reactant. So we reactant and electrolyte interact with anode, and then heterogeneously, and then reactant donate electron into the anode. So this process actually we call oxidation, and then simultaneously cathode donate electron into the our reactant or catalyst. So this process we call reduction. So normally anode so reduction is happening at anode, so oxidation is happening at anode, and reduction is happening at cathode. So this is the this process actually continue until reaction is complete. So that is the way how electrochemical reaction is working. So with that, let me discuss about some tools that we are using during the electrochemical reaction. So normally we are doing our electrochemical reaction in the electrochemical cells. There are two types of electrochemical cells. One is a undivided cells, and other one is a divided cells. Normally in undivided cells you can see two electrodes are in same container, but we have to separate two electrodes in divided cells. So actually those kind of electrochemical cells we can prepare in our laboratories also. But now there are new instrument has been introduced to perform this electrochemical reaction. So actually using these kind of instruments, so we can monitor reaction even at our home. So that is the wonderful development in this area. Another thing actually electrode. So electrode actually main part of the electrochemical cells. Normally carbon based electrode have been using because of this low cost. And actually here I have listed few examples that are nickel or platinum or zinc electrode. So with that, my next thing is actually solvent. So usually, so every most of the circuit should have a conductivity, higher conductivity. So without higher conductivity, so it's very difficult to continue the electric circuit. So here also same. So we have to increase conductivity of our solution. So for that purpose, we have to dissolve all reactant, catalyst, and also electrolyte into the using good solvent. So we can use actually polar aprotic solvents such as THF, DCM, acetone, DMA, acetonitrile. Those kind of solvent we can use for these electrochemical cells. Another thing actually electrolyte. Electrolyte actually, as I mentioned earlier, so we are using charge species to continue our electric circuit. So generally ammonium based or alkyl metal based electrolytes are commonly used for as ammonium or alkyl based metal are commonly used for the assay electrolyte. So here I have listed few examples that we can use as electrolyte. With that, actually I would like now introduce my main topic, electrochemical CH activation. So as I mentioned earlier, so we are going to access CH bond using electricity. So electricity as normally, so this is strategy chemical oxidant have been using, but now we are using electricity. So electricity as a green oxidant. So actually in this approach we can have sustainable CH functionalization. So that is the main advantage of this strategy, and also we can control the reactivity using potential, oxidative potential. And another thing, actually normally this kind of strategy, so we can decrease, I mean we have mild and selective reaction condition. So we can use this mild reaction condition to for a late stage functionalization. So as you know, late stage functionalization so has many functional groups. So if we are using mild condition, so we can minimize side reaction and also waste generation. So that's the one other advantage of this electrochemical CH activation. Another thing, actually, so we are using electron as a reactant and source of energy. So therefore we can increase atom economy because of this reason. So when we consider about the industrial approach, industrial scale development, so we have to consider those kind of things. So with that, actually there are many examples has been demonstrated with different transition metal catalysts like a palladium, ruthenium or rhodium, cobalt, those kind of things. In my next few slides I am going to discuss about few examples that related to this chemistry. So with that, is my first example. This is my first example that related to electrochemical CH activation. So here, actually this one published in 2007. Actually they use they have done CH alkylation, but here actually you can see they have very less substrate scope, poor substrate scope, but you can, this is a very early CH functionalization with electrochemical approach. That's why actually they don't have that much broad substrate scope. So you can see they have used electricity. So you may wonder why they have used this benzoquinone. So that's explained actually in this mechanism. So in the first step you can see we have active catalyst and then substrate coming in. So you can see now palladium and this aromatic C carbon has new bond. So that means this CH bond has broken. So that's the step we call is CH activation. So and then our next second substrate is coming in and have insertion, and then with beta hydride elimination we can get our desired product. And then we have reductive elimination to have palladium 0 species. So actually in this step we have to oxidize this palladium 0 species up to palladium 2 because of the we need to continue our catalyst cycle. So actually in this step we can use electricity to do this oxidation, but unfortunately this palladium 0 species and anode cannot interact with each other. Therefore they have used actually this benzoquinone. So then benzoquinone oxidized can be oxidized. So this palladium 0 species can be oxidized by benzoquinone, and then we can continue our reaction cycle, catalyst cycle. So actually you can see benzoquinone, when benzoquinone sorry, palladium 2 species, when palladium 2 species oxidized, simultaneously benzoquinone reduced to hydroquinones. So and then using metal, so using electrochemistry, so we can oxidize this hydroquinone into benzoquinone. So that is the electrochemistry coming into the story. So as you can see here, actually in this paper they couldn't directly apply this electrochemistry into this palladium catalyzed CH activation, because because of this is very early example, and they couldn't actually, even they couldn't completely remove the chemical oxidant. With that, actually next example, again with palladium catalyzed CH functionalization, but here actually you can see they have done CH methylation with electrochemistry. So in this system actually they don't have any chemical oxidant, but if you remember even previous slide I have mentioned they have used 10 catalytic amount of chemical oxidant. They have actually demonstrated bunch of substrate with higher yield, and in this step, this system they use electrochemistry to do the CH functionalization. Actually this same methylation has been done previously using chemical oxidants such as copper or benzoquinone. So now we don't need to use this toxic chemical oxidant. Now we can use electrochemistry to do this CH functionalization. So with that, I would like to discuss the mechanism for this CH functionalization. So you can see palladium, this is our active catalyst, and then we have substrate coming in to occur CH activation. Substrate coming in and then coordinate with the catalyst, and then next step actually CH activation. So this dimer actually they have isolate and characterize because they have isolate because they need to confirm this catalytic cycle. So actually next step you can see second substrate coming in, and then now this palladium 2 species directly oxidized into the palladium 4 species. So that is the place we are using our anodic oxidation. Previously actually we could previous system actually we did this anodic oxidation with redox mediator, but now in this step actually this paper we don't need to use this chemical we don't need actually we are using we don't need to actually use chemical oxidant. So and then actually with higher oxidation state palladium species can be reduced with reductive elimination, and we can get our desired product. So if you remember previous report, so they have this electrochemical oxidation after reductive elimination, but you can see now here we have it before reductive elimination. So this is actually two mode of CH activation mechanism. So it can be actually it will depend reaction condition. So that's why there are two mode of mechanism. Another one is rhodium catalyzed CH functionalization. So rhodium, so this is the first example with the rhodium catalyst CH functionalization with rhodium catalyst. So you can see here actually they have used a very weak carboxylic acid directing group, but previous report for with palladium as palladium catalyst, so they use a very strong directing group like amide oxide ether, but here they don't need to use that kind of strong directing group. And Actually, other good thing is this system. So you can see they have synthesized very sensitive and valuable ester derivatives with a very high yield, and also they improved this system to get the benzamide derivatives and also benzyl pyrimidal derivatives in pyramid pyrimidal indole derivatives. So with that, my next example actually ruthenium catalyzed CH functionalization. So generally ruthenium is known to have chemoselective sustainable CH functionalization. So actually here, so you can see they have alkylation, they have alkyne annulation product with the electrochemistry. So but previously same reaction has been demonstrated using chemical oxidant, but now we don't need to use, we just use electrochemistry setup. So they have demonstrated big substrate scope with different what's the called different substitute. So with that, I need to discuss about the mechanism for this reaction. So you can see in the first step substrate coordinate, and then CH activation happen, and then after that we have second substrate coming in to get our to insertion, and then after insertion, so you can see reductive elimination to get our product. In this step, ruthenium 2 species is reduced to ruthenium 0. So then we can oxidize this ruthenium 0 species up into ruthenium 2 to continue our catalyst cycle. So this can be done actually using anodic oxidation. So here this is the place that we are using electrochemistry to access this inner CH bond, and then actually they have applied this strategy to synthesize drug molecule. Its name is a base doxyphene. Actually this one commercial available drug molecule that used for as an anti-osteoporotic drug. So that's the big advantage of this system. So you can see we don't need to use this chemical oxidant to synthesize this kind of drugs molecules, and it's a that's the great advantage of system. Last not least, I would like to talk about cobalt-catalyzed CH electrochemical CH functionalization. So as I mentioned earlier, the previous few slide I have talked about um, uh, 4D expensive 4D transition metal electrochemical CH functionalization, but those 4D transition metals are very expensive, so that's why people were looking for alternative for this 4D transition metal. So actually when we compare with the price with those, it's a very low price. Cobalt has very low price when we compare with others. So and also cobalt is a first 3D earth abundant transition metal. So that's the therefore we can replace that very expensive substrate with this very expensive catalyst with the low cost catalyst. With this actually this is the first electrochemical approach for the cobalt catalyzed CH functionalization. So you can see they have used electrochemistry to access this CH bond. So and they end up with different kind of ether derivatives using this strategy. So here actually here good thing actually you can see this system has actually can be done in the room temperature. So that is actually very important when we talk about the late stage functionalization, as I mentioned earlier. So we we are doing those reactions in room temperature. So that can be that is a great opportunity to decrease the side reaction. So with that, I would like to I would like to give future direction before I summarize my talk. So as uh, there are a bunch of development has been demonstrated related to this chemistry, but still there are some challenge to overcome before it adapted to industrial settings. So one actually thing one thing actually you can one challenge is actually recycling electrolytes. So uh, although CH functional electrochemical CH functionalization is a sustainable approach, but still we cannot reuse electrolyte. So that's the problem with electrolyte. So we have to develop new method to reuse this electrolyte uh, and then reuse electrolyte and then separate from the reaction mixture. So we need to find the best we have to find best solution for those. This is to recycle electrolyte. Another one is actually enhances selective CH functionalization. So actually when we synthesize uh, drugs molecules, so we have to consider about the enhancer selectivity. So for the enhancer selective CH functionalization, there are few example has been demonstrated, and still need to be developed many of things. And other one actually electrode. So as we know, electrode is consuming during the redox reaction. So finding new electrode, finding new material for electrode is would be wonderful. Another one actually artificial intelligence. So organic synthesis has been uh, connecting with artificial intelligence. So as also here actually we can use this electrochemical CH functionalization can be combined with artificial intelligence. Then we can predict actually uh, new reaction and also product. With that, I would summarize my talk. So in this video actually I talk about sustainable approach for the electrochemical CH activation. That is a powerful tool for power tool for molecular synthesis, and also early example that has been demonstrated with the palladium. So very early, so still we have to use chemical catalytic amount of chemical oxidant, but late actually we don't need to use even uh, catalytic amount of CH catalytic amount of chemical oxidant. So uh, another one actually uh, the developing earth abundant cobalt catalyzed electrochemical CH functionalization. So that is actually very big development in this area, because we can introduce this cost effective method into the industrial scale, and we can develop further we can have further development in with this new area. So with that, thank you very much for your attention, and we will meet with another video, and see you later.